So continuing off the previous video, now let's try to find the double integral described by the surface S of the dot product of the vector field f and ds. So this is known as the surface integral of f over s, or it is also known as the flux of the vector field f across the surface S. And so let's say we are given a equation, well, z equals some function, let's just call it g, but it has to be in terms of x and y. And we're also given a vector field f, which has the components p times I plus q times j, and then plus r times k. Then the formula to evaluate this double integral, or to evaluate the flux of f across S, is going to be equal to the double integral described by the region D of negative p times the partial derivative of the z equation. So we're going to take the partial derivative with respect to x minus q times the partial derivative of the z equation with respect to y plus r, and then times dA on the outside. Now let's say instead of a z equation in terms of x and y, let's say instead we get a y equation. So y equals another function, let's just call it h, this time in terms of the other variables x and z. Then we can simply just replace those partial derivatives in the formula with the partial derivative of y. So we can rewrite it as negative p, this time times the partial derivative of the y equation with respect to x, and then minus q times the partial derivative of y with respect to the other variable, which is z, and then we can add the r. And that's how we can use the formula if we're given a equation in terms of y equals rather than z equals. Now let's say instead you're given a vector function r in terms of two parameters u and v. Then the formula you can use to evaluate the surface integral or the flux integral is going to be the double integral described by the region D of the dot product of the vector field f and the cross product of r sub u and r sub v. And then we have dA on the outside. Now we won't be using this formula, but this is the main formula that we got to focus on for this video. Now I'm just going to go ahead and draw a surface here. Now similar to how in Green's theorem we had positive and negative orientation, when we evaluate surface integrals or flux integrals, there's also unit normal vectors, which are vectors that are perpendicular to the surface at specific points on the surface. Now if these unit normal vectors are facing upward, then we have upward or positive orientation. And if the unit normal vectors, let's say, are facing downwards, then we have downward or negative orientation. And so the only difference between positive and negative orientation is that with negative orientation you just have to have the negative, or you multiply the double integral by a -1. So for this next set of problems, let's go ahead and evaluate the surface integral. So we have the double integral described by the surface S of the dot product of the vector field f and ds for the given vector field f and the oriented surface S. In other words, find the flux of f across S. For closed surfaces, use the positive or outward orientation. So for number 1, we have the vector field f of xyz equals xy times I plus yz times j plus zx times k. And it's giving us that S is going to be the part of the paraboloid, z equals 4 minus x squared minus y squared, that lies above the square. And the x bounds of the square range from 0 to 1. The y bounds range from 0 to 1 as well. And it has upward orientation. So notice we do have a vector field, we do have a z equation. So we can use the formula where we have the double integral described by the region D of negative p times the partial derivative of z with respect to x minus q times the partial derivative of z with respect to y plus r, and then times dA. So once again, p is going to be the x component of the vector field, so that's going to be x times y. Q is going to be the y component, and then r is just going to be the z component of the vector field. So let's go ahead and rewrite this formula. So we have the double integral of negative p. Now p is going to be once again x times y, so negative x times y times the partial derivative of z with respect to x. So we go ahead and take the partial derivative of 4 minus x squared minus y squared with respect to x. We then get negative 2x. And then we have minus q. Now q is going to be the y component of the vector field, y times z, times partial derivative of z with respect to y. So that's going to be negative 2y. And then we have plus r, and then r is going to be z times x. Now I'm just going to go ahead and simplify this. So negative xy times negative 2x, negatives will cancel, and so we'll get positive 2x squared y. We have a negatives will cancel here as well. So plus we have 2y squared z, and then we have plus z times x. So now I'm going to go ahead and put that under the double integral here. If I go ahead and delete this top portion. Now realize that we can only have two variables since we're taking the double integral, but here we have three variables. So what I can simply do here is wherever we have z, I'm going to eliminate that and replace it with the equation that is given to us, 4 minus x squared minus y squared. So we have everything just in terms of x and y. So here I'll replace it, and here I'll replace it as well. So if I go ahead and we have 2y squared times z, z once again is 4 minus x squared minus y squared, and then plus z times x, so we have 4 minus x squared minus y squared times x. Now if I go ahead and distribute over the 2y squared, you'll get 8y squared minus 2x squared y squared, and then minus 2y to the fourth. And if I go ahead and distribute over the x, we will get plus 4x, and then minus x cubed, and then minus xy squared. And don't forget we do have the 2x squared y up front, then I'll just go ahead and add it. So since there are not really any common terms here, I can't necessarily simplify this, so now I'm going to put this under the double integral, so that we have simplified it all the way. Now realize the x bounds go from 0 to 1, the y bounds go from 0 to 1, so let's just go ahead and put the x bounds first. So put dx on the outside, and then dy, or dx on the inside, and dy on the outside, and the y bounds go from 0 to 1 as well. Now keep in mind, since it does have upward orientation, we can keep the double integral as positive, we don't need to multiply by -1. So now let's go ahead and evaluate. So I'm going to evaluate the inner integral first, this time with respect to x. So the integral of 8y squared with respect to x is going to be 8y squared times x. We have minus the integral of 2x squared y squared is going to be 2x cubed over 3 times y squared, minus integral of 2y to the fourth with respect to x is 2 to the y to the fourth times x, plus the integral of 4x, which is going to be positive 2x squared, minus the integral of x cubed, x to the fourth over 4, minus integral of xy squared is x squared over 2y squared, and then plus the integral of 2x squared y is going to be 2 over 3 x cubed times y. So now we can go ahead and evaluate from the x bounds of 0 to 1. So when I plug in 1 for x, we will get 8y squared minus 2 over 3 y squared minus 2y to the fourth plus 2 minus 1 over 4. We get minus 1/2 y squared, and then plus 2/3 times y. Now minus, when I plug in 0 for x, but the good thing is when I plug in 0, everything will just be 0. So that will cancel out. Now since we do have a couple y squareds here, I'm going to go ahead and simplify and sort of subtract those terms. So I can go ahead and find common denominators here. Now a can be written as 24 over 3. So then 24 over 3 minus 2 over 3 is going to be 22 over 3. So we have 22 over 3 y squared, and then we also have a minus 1/2 y squared. So 22 over 3 can be written as 44 over 6. So then 44 over 6 minus 1/2 can be written as 3 over 6 is going to be equal to 41 over 6. So we have 41 over 6 y squared. So then I can go ahead and cross those terms out. And so I can go ahead and simplify 2 minus 1 over 4. 2 can be written as 8 over 4, so 8 over 4 minus 1 over 4 is positive 7 over 4. We do have that minus 2y to the fourth, and then we have plus 2/3 y. So now I can evaluate the outer integral. Remember the outer integral is also from 0 to 1, this time with respect to y. So the integral of 41 over 6 y squared is going to be 41 over 18 y cubed, plus integral of 7 over 4 with respect to y is going to be 7 over 4y, minus integral of 2y to the fourth, negative 2/5 y to the fifth, and then plus the integral of 2/3 y is going to be 2 over 6 or 1 over 3 y squared. So now let's go ahead and evaluate from the y bounds of 0 to 1. So when I go ahead and plug in 1 for y, we will get 41 over 18 plus 7 over 4 minus 2 over 5 and then plus 1 over 3. Minus when I plug in 0 for y, and then that'll just be 0, so it'll all cancel out. And so we're left with these four fractions here, which we can go ahead and combine. So negative 2 over 5 plus 1 over 3, I can rewrite it as negative 6 over 15 plus 5 over 15. So that's going to be equal to negative 1 over 15. And so what we have left is 41 over 18 plus 7 over 4 and then minus 1 over 15. I'm just going to go ahead and use a calculator for this. And so when you use your calculator, you should get the final answer of 713 over 180. So now for number 2, we have the vector field f of x, y, z equals y times j minus z times k. And it's giving us that S consists of the paraboloid y equals x squared plus z squared. And for that paraboloid, the y bounds go from 0 to 1. And the disk x squared plus z squared is less than or equal to 1. And it's giving us that for the disk, y is exactly equal to 1. Now, I just wrote down the formula that we used in the previous problem. But notice, in this case, we aren't given z equals some function. We're given y equals some function. So it's better to put everything in terms of y. So we can rewrite the formula as the double integral described by the region D of negative p times, and this time it's not going to be the partial derivative of z, it's going to be the partial derivative of the y equation with respect to x, minus q times the partial derivative of y with respect to the other variable. So we already did x, so now the other variable is going to be z. And then we have plus r times the entire thing times dA. So let's go ahead and rewrite what's inside of the formula for the double integral. Now notice for p, there is no x component because p is really with the x component, because p is associated with the function in front of the I unit vector. Since there is no I unit vector, we can say that p is going to be 0. So we have basically 0 times partial derivative of y with respect to x. It's just going to be 2x minus q, this time it's in front of the j unit vector, so that's going to be y, times partial derivative of y with respect to z is going to be 2z. And then we have plus r, but this, be careful here because r is actually not positive z but negative z because we have minus z times k. So it's basically going to be minus z. So the 0 times 2x will cancel, and so we're left with negative 2yz minus z. Now remember that the y equation that was given to us is in terms of x and z. So we also have to put what's inside the integral in terms of x and z as well. Right now we have it in terms of y and z. So let's go ahead and replace y with what it's equal to, x squared plus z squared. So we have negative 2 times x squared plus z squared times z minus z. So rewriting it, I can rewrite it as negative 2 times z times x squared plus z squared, and then we have minus z, and I can go ahead and put that now under the double integral. So if I go ahead and remove that, I can go ahead and put that under the double integral. And so now we need to find the bounds of integration. So in order to find those bounds, we need to basically graph this disk. Now if you look at just the equation x squared plus z squared equals 1, we're basically looking at the equation of a cylinder. Remember, with the equation of a cylinder, whichever variable is missing, that's going to be the axis of the cylinder. Since the y variable is missing, the cylinder is going to be on the y-axis. So if I go ahead and graph this out, x, y, z axis, the cylinder is basically going to be on the y-axis, and it's going to have a radius. Well, the radius squared is 1, so the radius is just going to be 1 as well. So r equals 1. But now it's telling us that it is a disk with the y value only being equal to 1. So we're basically looking at one cross section of the cylinder, which is a circle, but only at the y value of 1. So let's go ahead and say, if I use a different color, this is the y value of 1. And if I erase that, if I erase every part of the cylinder and just leave the cylinder, that part of the cylinder that is left at y equals 1, then we basically get a cross section of a circle. So if I redraw that here, we're basically going to get a cross section of a circle, and it's still going to have a radius of 1. So if we go ahead and look straight towards the y-axis, we'll basically get a view something like this, where the region is obviously a circle with a radius of 1. And then we're going to have the z-axis that goes vertically, and then the x-axis that goes horizontally. Now, since the region we are dealing with is a circle, it is better to obviously use polar coordinates to evaluate the double integral. So we can say for the r bounds, or the bounds of the radius, goes from 0 to 1 since the radius is 1, and the theta bound, since it's a complete circle, goes from 0 to 2 pi. So now we need to go ahead and convert also what's inside of the integral into polar coordinates as well. So for x squared plus z squared, realize that the circle is going to be on the xz axis. So it's treated the same way as if it were on the xy axis, where if x squared plus y squared equals r squared, then x squared plus z squared will also equal r squared. So we have, this is going to be r squared. And if the z-axis in this case is sort of acting like the y-axis, then z is obviously just going to be equal to r sine theta. So we have negative 2 r sine theta times r squared, and then minus r sine theta. Now don't forget, whenever we convert to polar coordinates in double integrals, we do have to multiply by the extra r variable. So what we have left is going to be negative 2 r to the fourth times sine of theta minus r squared sine theta. So now to simplify just a little bit, I'm going to go ahead and factor out sine of theta. So we get sine of theta times negative 2r to the fourth minus r squared. So if I go ahead and delete the top row here, now we can go ahead and put that under the double integral. And so once again, our r bounds are from 0 to 1, theta bounds are from 0 to 2 pi. So let's go ahead and just integrate with respect to r first. So from 0 to 1, and then theta from 0 to 2 pi. So d theta on the outside. So now we can go ahead and evaluate the integral. So if we're going to integrate with respect to r first, then sine of theta is just a constant, so that we get sine of theta times integral of negative 2r to the fourth is negative 2 over 5 r to the fifth. We have minus integral of r squared is going to be 1 over 3 r cubed. And we can evaluate from the r bounds of 0 to 1. So when I plug in 1 for r, we get sine of theta times negative 2 over 5 minus 1 over 3. So negative 2 over 5 can be rewritten as negative 6 over 15. Negative 1 over 3 can be written as negative 5 over 15. So then when I subtract those fractions, we get negative 11 over 15 times that constant sine of theta. So now I can evaluate the outer integral from 0 to 2 pi, this time with respect to theta. So negative 11 15 is a constant, and the integral of sine of theta is going to be times negative cosine theta. Realize that negatives will cancel, and so we get 11 over 15 times cosine of theta. So now we can evaluate from the bounds of 0 to 2 pi. So we get 11 over 15 times, well then cosine of 2 pi is 1, minus cosine of 0 is also 1. So then 1 minus 1 is 0, and 0 times 11 over 15 will be 0. And that is actually the final answer.